So I forgot to pull out your chat here. Let's see. So let's see. Let's us do some say. Oh yes, the first thing. Let me show the. As I said, the. Oops, I want to pull. Oh, okay. Oh, yeah, I guess I pull that up. I have a kind of. Oops. Okay. I cannot. Yeah, you don't know what I'm doing. Actually, I'm trying to move windows around. So yes, let me maybe start a new. I guess I used Untitled before. Yeah, I think I probably can use this again. So and okay, maybe I'll just show like the homework like what I'm kind of expecting. So it's not perfect. Like I guess I maybe you can I'm not sure you can see the low pass image. Maybe you can try to move away from the screen, like somehow like okay, maybe this is a question. Like can you guys I see what's the low pass there? Like, as a question one, like to see like if anyone is around. Uh okay. Yeah. I guess you yeah, it's not very clear. Maybe you need to okay. You need to walk back. So you need to walk back to see that. Okay, let me adjust it a little bit, make it more okay. Yes, does it get more obvious? Uh not the oh okay. I probably should scale down this. Maybe I change lower this filter. Is yeah, is that more clear now? I guess probably like it's going to see yeah. Yeah, now it's like yeah, it's kind of like so yeah, I'm expecting something like that. Like it's not perfect. Okay, it depends because I just arbitrarily pick two stock images. Like if you pick like images like that, it's more what I should say like don't cover like one cover the others, then maybe it's more apparent. And also like you can adjust the filter strength here. So I here like I adjust the kind of like the filter strength for the low pass, like for the dog, like maybe I can make the dog stronger here, like it's like super strong, and make the cat like kind of like also the high pass stronger here, or actually I should say the high pass filter weaker there, then it become more apparent. So and also you can adjust say how how much they added together as well. So um that would be some adjustment. So I guess I may illustrate like how do you do track bar like in OpenCV here. So it's convenient. And I guess it's I for the second part that I want to use I mean generate a composting image. So that would be like extra credit if you add a track bar, like if you remember like what I mean. Like what's that? I think it's here. Let's see. Oh, I need to shut this first. Okay. So so what I mean is like this track bar will give you extra credit, just like he's showing that like uh I'm like with different level of decomposition, right? Basically. So it's good to It's actually easy to do something like that, and like some tools like that is convenient for debugging. Like for example, like when I generate a hybrid image, if I just like type in try to different parameters, like each time I modify the parameters, it can take lots of time. But instead, like and how to get hybrids. Uh, at a low pass. Yes, actually, okay. You cannot just you need to weight them because I um for the for OpenCV like you only have the precision like 8 bits, right? So if you just use the filter by itself, it will give you integer. So therefore, if you just add them together, like they will overflow. So something like, let me show that hybrid again. So for example, like if I here you see like I add the dog and cat, like I think dog is like 0.5 multiplied by 0.5 and cat multiplied by 0.4. So if I just add them together, like it will totally saturate the, oops, I don't know. Maybe this is, yeah, it will totally saturate the image. So I don't know why the dog disappears somehow though. But what I mean is like you cannot simply add them together. You need to weigh them like before adding them. Yeah. Huh, that's very weird. Oh, hmm, this is interesting. I don't know why it actually disappear if I add the weight to be too large. Yeah. So, okay. Okay. As I said, like maybe. Okay. Yeah. Yeah. And we were talking about warping last time, right? Maybe I show some also demo for warping. Let's see. This is rotation, right? So, here I kind of like rotating, and this is I'm showing the matrix as well. So by the way, like probably you won't remember about that, but uh know that like here when I have a positive angle here, so now I'm kind of like rotating like positive 15 degrees, but I'm actually the you remember like okay maybe I show a Suno somewhere like here. Or here is like okay I should probably like maybe go to some pages that doesn't have anything. Yeah, maybe here. So let's see, I can write. Yeah. Remember, like last time we say like if I do a rotation somehow, I have some rotation matrix. Let's say this an image. I cannot write straight somehow. I can use this, I guess. Oh, this is still like, huh? Okay. So if I rotate by like theta degree, something like this, right? This is theta degree. So this is using a matrix or something like this way. Maybe I call it R theta or something like that. Something like cosine theta minus sine theta, cosine theta. One, something like that. If you use the homogeneous coordinate. Now the if you I have the same R theta here, but as you see, my theta here is 15 degrees, but I am kind of like rotating in this direction instead. So, okay, maybe it's a question that is it a bug or not bug or not? Yes, bug. No, not a bug. I'm using the same matrix. Basically, I'm saying like I'm using the matrix that we showed last time. This one. but now I'm rotating like in when I have like theta positive, basically I said theta is equal to 15 degrees. Suppose supposedly or supposingly that like this theta should, I mean, it should rotate counterclockwise, right? But somehow I have the image rotate clockwise instead. Why is that? Is that a bug or like or like or I shouldn't say is that bug. Is that normal? Is that like some yeah? So I guess it's hard to ask like why is so, but uh okay, yeah, it is a lot of bad. Know that like you, what we discussed last time, we used the usual Euclidean coordinate convention that is like x here, y is going up, right? But in computer graphics and so on, like when you do open series and so on, like x is this y direction, but y is this direction. So therefore, like if you say rotate by theta degrees, actually this angle here. I mean, like because like this would be a positive y, right? So therefore, like, you will rotate like this way. So this is an example of rotation. I can show, for example, uh, shearing here. Let's see, let me try. Wait a sec. Wow, this is so dark. Which camera is using that? Let's see. Oh yeah, I have this. Okay. I think it's like this camera. Okay, it's okay. I don't know what you're seeing, but this give the, so if I do shearing, it's like that, right? So you see, I'm kind of like changing is this these two parameter here to get the shearing effect here, right? So okay, and I may do a do a scaling as well. So so you see, like scaling, I just have this what's that? The diagonal, like it's like this. If you remember, the scaling matrix is just you have oops, this maybe I call the scaling matrix S. So this okay, maybe I just wait. So it's a scaling by x, then x-axis scaling by y-axis, and then I just one. That will be the scaling matrix. Okay, I guess okay, let's do it from scratch. Maybe try one of these. Maybe I just try the rotation, like to demonstrate how to use the track bar, like do a little bit open series, like we didn't do open series for a long time. So so, oh, how do you guys like that? Like if I do that, or like you prefer to have just uh mm, I mean with I mean the documentation yourself, like uh, oh, okay. I guess the only way to make you guys like answer a question is like this as I literally make it a participation question. So eh, do you want to do you want me to go through the track bar like or like this cvui, give an introduction of cvui? So like you see like I use this track bar and so on, right? This is using the UI of cvui. Oh, okay. Yes. Okay. Okay. So, so it looks like yeah. Okay. It looks like people. Okay. So you guys seems to good with that. So let me just give a little bit. Uh, this maybe I start with like okay, open series just like capture a camera first as usual. Then I capture something and then rotate maybe. So let me define. I turn off my Cantonese input here. Uh, so let me define window name first. Window name, maybe rotation. So as usual, I have this while true loop here. and I don't always remember this break condition, so I will just copy that. So if my basically wait key something, I don't wait, or I can wait a bit longer actually, maybe I waited 30 millisecond or something like that. So if then I cv2 destroy a window, so I don't have a Windows here yet. Maybe I, all right, that's fine. Actually, yeah, let me show something anyway. So maybe I add this cap is 32. What's that video capture? What's my camera here? I think I'm each time I plug in the cameras, they change the. It's okay. I just put in a number. If it doesn't work, I change to something else. Then maybe cap midway somewhere, and I will show the image. Window name. I need to put a I call a frame here. Okay. By the way, so this is a very much I would say uh I guess basic to many of you, but it's good to you write code like you just write couple lines of code and then like test it, because especially when you're writing script like for example like I mean interpretable languages like for example MATLAB, Python, you don't need to compile. It doesn't take time to really run your code to test it. I mean it's much easier that like you kind of stop every once in a while then to what's that like frame is not there. Oh, okay, yeah, I forgot to return there. So that's much easier like until you write I mean like 100 lines of code and then you want to figure out like what's going on like when it doesn't work. Maybe it's not image show. Let me make sure. Or just show. Yeah, it's image shows. So what's wrong? So let's see. I don't have the frame there. I probably need to run again. So okay, now I got it. So that we as usual. Now let me I need to get a filter. Right? Let me just do this rotation with some filter here. So I have like filter is as let me initialize something. For the cvui, I need to uh, store it as a list to access it. It's a little bit weird, but you can think of like programming in C. I have a pointer instead of like, I mean, what's that called? Like, access the value as pointer instead of like access using as a value. I mean, if you're not sure what I'm talking about, it doesn't matter. But this you just can think of this as a convention. So let's say I start with some theta, it's like 30 degrees. Now I try to rotate that. Like first I want to generate the uh, the matrix, right? So let me define a function to generate the matrix. Let's say I call it like just M, maybe rotate M. And then like I have the input like theta there. Then the rotation matrix will be maybe I should convert it to degree to radian first. So I have maybe maybe I just write like that. It's okay. TH is equal to TH times pi. I need to import numpy, I guess. Times pi over 180 degree. So that would be my theta. Then my rotation matrix is just what I have like cosine theta. It's actually it's a lot of typing. Maybe I just define cosine and sine first. Cosine would be like cosine theta, and sine is just s, and be sine theta, let's say. Then I will have like c and minus s, and then 0, and then second row is like s, c, 0, form it like 0, 0, and 1, right? Something like this, right? I think I'm doing okay, right? So yeah. I may try it out somewhere else. Let's see. Okay, okay, I did forgot to cap relief, so every once in a while it just. So is that, do I have the window here? Yeah, okay. That, yeah, now it's okay. So let me try my rotation, something like makes sense first. Maybe like 10 degrees, I got something like that. It looks good. You probably want to try some like special cases, make sure things is okay, right? So if like it's 0 degree, then it's identity matrix, right? Definitely is okay. So if like it's like 180 degree, it would be kind of flip, right? So you see like I have yeah, let's see, 180. Yeah, I guess like X and Y would be flipped, right? So is that, yeah, I think so. So then you have -1 here, right? So here it's not 0, but it's very close to 0. It's good, right? This is supposed to be 0, but yeah. So I have my rotation matrix. It seems to be good. Now then let's try to rotate a little bit. So I have the in got the frame, right? Before I put out the frame, let me rotate that. Maybe I just rotate by th. So frame is cv2 wall perspective. No, it's not. I didn't do anything yet. So that's no magic. So this is a pure Python. So you cannot just have this th. I didn't do anything yet. So I have this frame here. I just define a variable th, but I didn't use it yet here. Right? So now I am going to rotate it. Right, rotate with this angle here, th. So I have this like warp per step perspective. I think my spelling is wrong. Yeah, perspective. So this basically you warp the image with your perspective matrix. So it's generic. So you if you have like a different matrix, I say like any perspective transform is okay. For example, I can it's like any feed by feed transform, like perspective transform, as we described last time. You can use this warp perspective to warp the image. So I have this is I use this rotate m, let's say this th 0. Note that I need to do that because it's a list here. This is a convention that for cvui. So basically like that's how they are able to modify yeah the value. As you see, like so I basically make a list, so therefore like here I access the first element of that list. It's kind of something dummy. Yeah, it's kind of dummy, but like yeah, so uh that's the only thing like maybe it's a little bit weird, but other than that everything else is quite natural. And for the warp perspective, we need to define the image size somehow. So maybe I can use the original size there. So I have like maybe uh, the size. Okay, I always don't remember like okay, let me try. So I will take the first two value here. So it may be okay. Let's try that. And yeah, it looks like yeah. Okay, yeah, okay, it's all doing okay. So I have like warp this image. Oh yeah, but the shape here, like I guess it's like the x and y here is like flip. So therefore, like I maybe I want to reverse the order. If see if I can do that, something like that. Reverse. No, I cannot actually because it's expecting a tuple. Um, so I guess I need to do it explicitly. It's okay. Probably will work like that. do one again, I guess. Yeah. So yeah, now it's okay as expected. Um, and now let's do the cvui first. This is very nice, very simple. So of course I need to import the cvui, right? Cvui, and then I need to init that. Uh, init the window names there. So I will just init the window name. And then the only thing I need inside here is like, okay, create a chat box. Here I'm doing something that like I said it's not good to do, but uh what I mean is it's not good to hard code that. But usually like hard coding like something like this, for example, if you have like a UI, yeah, it still is actually like good practice. But here like I'm doing that for the time thing. So I will just say, so I will hard code the location. So I'm going to generate a chat bar that have the X locate. Or first I need to specify like chat bar on where. So I have the chat bar on this frame here, and then the location is maybe I just put it here. So I guess anyway like you will see uh X location is 10, maybe Y location is 10 again, and the length of the chat bar maybe bar location is bar location Y, bar length, let's say 100. I'm not sure it will be too long. It's okay. And then I will have so bar X location, bar Y location, bar length here, and now I then next thing I put into the variable here th here. So you see why I need to create this as a list, because otherwise you kind of like this function cannot return back. I mean modify this value, right? So uh I this is I'm not a CS major, like probably you guys can really correct me like this uh this is what uh uh okay, anyway, I'm not going to try even. So okay, anyway, so then the next two variables I need to specify the max and mean, maybe like uh mean theta here is 90, mass theta here is sorry, mean theta minus 90 make more sense, right? Mass 90 or something like that. So mean theta, mass theta. So that's it. Basically that I create a chat bar, and then the only thing left I need to do is before I'm showing this frame here, I need to run this update thing. So then it did all the magic basically. So supposing it should work. So now I have this chat bar here, and I can adjust this thing like with the chat bar as well. So yeah. So of course you can create more chat bar. For example, if I have another variable, you can add another chat bar. There's other like um, simple like UI available. You can like just uh, all right. So oh, okay, yeah, I need to break this first. Yeah, you can, for example, like just list it out to see like what's available. For example, like what that chat bar task, you can create some tasks, I guess. There should be some button, like for example, some button, the chat box, and so on. Some very simple UI like you can do like very easily. So you can even create an app like very basic elementary app like app prototype like with using a UI like this, and then like this is like do this kind of like if you have a startup, do minimum viable product, right? So you just want to do something and absolutely basic and show it to the angel, and then I say, okay, this I have this, and then okay, if you fund me, I will get someone to just brief it up, like make the UI beautiful, and this you can, yeah, this kind of like is actually very important, like just able to get something minimally one thing that like to show someone. So okay, I guess that's it like for a very simple introduction of cvui. So and so uh, I assume you guys have no questions. So then like what I'm going to do next, then um I'll just go back to talk about health corner detection. So this is like the things, the main things I like to talk about today. So yeah, sure. Like if you like it, like we can. But I actually like OpenCV is quite simple. Like I shouldn't say that, but I mean like uh yeah, of course, like there's lots of like detail, but like if you just like do something minimal, like it's actually not too difficult, right? So it's always like you don't try to learn. I mean, read the all, I mean, the entire API like from uh, I mean page to page, right? From top to I mean, what's that phrase say like uh yeah, cover to cover because you it is not necessary. You want to just like learn the minimum that you can make, try to make yourself like your hands dirty and then like work on like whatever like some tiny small like project programming experiment because like everyone is have like I don't know like limited capacity, right? So if you try to like just memorize the whole thing, it doesn't. I mean, it's meaningless. Especially in this day, you can just quickly Google stuff. Just learn the stuff that you can do the minimal. Then like if you need more, then learn more basically. I mean, in terms of the API, of course. So um and so I'm going to talk about Harris corner detector. Uh, maybe I'm still like create another Suno here. But let me go to the slides a little bit and then use some equations. Use the Suno to write equation. I guess it's easier to follow. So so basically like corner detection is like we talked about edge detection last time, right? So corner detection you can think of like it's a kind of feature uh feature detection, so very elementary kind. Next time we'll talk like more feature detection or like local feature detection. Uh, for example, we will talk more detail like for safe feature like that is very popular in comparison. So but let's consider corner this time first. Like corner, we'll think of like how does something like contribute a corner. So you can think of like let's say have a very simple image here, right? Just white and black here. And if I move this patch around, right? Uh, here, like apparently is flat here. And I move around here, this is an edge. And then I move to here, it's kind of like can consider as a corner. And so like what correspond to corners? You can think of like one way uh, to quantify a corner is like let's look at say how if I move this window around, it will the value of this window change. Basically, like if I have this window here, the values inside this window, if I have a flat region, if I move this window around, basically the values inside that will not change, right? It will be basically if like it's all black, no matter like how I move around, the values inside this window will be the same. But for here, for the edges, if I move around like vertically, again, like it will be like this here, like in the flat region case, the value will not change. The values inside the window will not change. But if I move along horizontally, then the values will change significantly. And on the other hand, if I have a corner, then if I move around like in whatever direction, I'm going to have like changes in the values. So I can use this to quantify like whether somewhere is like likely to be a corner or not. Or like I can define some cornerless function somehow. So if I have this cornerless function is big, then like that would be like will be a corner. So that's will be the main idea here. So then I have this cornerless function can be like, okay, here I is just the image here. So as you can see, like I have the image that X, Y is just a pixel value, like the intensity at the X and Y, right? So W here is a window. So think of like if I shift the image a little bit, like shift by U and V, then I will have an image like IX plus U and IY plus U, right? Or like you can think of the pixel and X and Y will be shifted to X plus U and Y plus U, right? So then now if I have this quantity here, if I have the flat region here, um this will be just should be equal to 0, right? Because I move a slight U and slight V here, this value will be this will be these two values will be just the same, right, as we just mentioned earlier. And yeah, W is just the window we discussed earlier. So then if we look at this function here, this will be basically uh, a function that can specify the cornerless somehow that we just described earlier. That if like I have like different U and V values here. So let's say for okay, let me go back to here. So actually maybe it's still like it's easier to use Suno. Let me copy this image and then yeah, because I don't know why PowerPoint like this pen is so difficult to use and cannot support like Control Z. This is like so. I guess I make a little bit better. Copy this guy here. So let me maybe even I think I have a page with this. Oh, okay. Actually, yeah, that's fine. Let me use this and then copy this equation as well. Maybe. Okay. So what we are saying is that, right? So think of so okay, now I can write. So WXY is basically this window here. Okay, I cannot say that. Okay, this is the windows here. Now, if I for different U and V value, like it's something like uh for this guy here, maybe I should use a different color here. Like for this guy here. So if I take a U value, let's say this is U direction and this is the V direction here. So maybe I take a UV is equal to like 1 0, then it basically shift this patch by 1, right? So like I look considering a patch here is basically is essentially shifted by 1, and then I want to see like whether this shifted patch is the same as this patch, right? Then I compute the difference here and then weight the sum difference here. So for the flat region here, like I for different UV, it's not going to change, right? Now for this one here, okay, maybe just make sure you guys are following what I'm talking about. So E 10 maybe I make it this way. E01. So which one is bigger? Oh, I need to pull back the chat window. Okay. So is my question clear? So I have something like, okay, uh, uh, CO1 is bigger, you mean? Okay, my question is I have this E function here, it's like this, it's defined like this. So let me know if you don't know, like, I mean, like, is there anything unclear about this definition here? This W is like a Windows, you can think of this essentially like uh, W is, let's say, yeah, actually literally something like that. So I have like a W function like that. So here inside this window is one and the outside is zero. So essentially just like window out anything outside this way, not counting anything like outside the window here. And then I inside the window, I'm trying to find the difference of the shifted image compared with the my original image. And then I just say sum the square difference of all of them inside the window. Now, then I found this definition here. So let's consider this middle image here. And let's say this is the U direction and this is the V direction. So you can consider like U10 and U01, right? Like two different values here. Now the question is like which one is bigger? U01 bigger or like U10 bigger? So it will not be the same. So let's many of you have answer. So yes, actually, like it's converging to some uh to the correct answer now, because you still one is actually equal to zero. If this is the v direction here, if I move around here, like I move up here, this is still the same, right? This patch is still the same as this patch, right? So therefore, like if you think of the square difference, some square difference of these two patches will be the same. So E01 is actually equal to zero. But if you move around like E10, if I move in this direction instead, then this this patch, like the original, okay, I have like maybe I will draw it. So I have the original patch will be more or less like this way. And then I have the final patch is like this way. So if I sum the square difference, uh for this region here, that is zero, like for this region here is zero, but like in the middle here, like this two part, let me use again another color. So this part and this part won't be the same, right? So I if I sum the square difference, it definitely will be bigger than zero. So this will be bigger than zero, this will be equal to zero. So therefore like E10 is bigger. So and for corner, I guess it's apparent. I guess I don't need to ask another question for this one. I guess uh no matter like whether you move this direction or this direction, I mean like you have like UV, like for any UV you expect like it will be like bigger than zero, eh? Like because you no matter like how you shift around, maybe you can shift uh like horizontally to here, then the patch will be different, or like vertically to here, still the patch is different. Or I mean, even like to diagonally, like both U and V is like positive, and also like it will be different, right? So therefore, like uh, I will have like E, U, and V. Okay, actually, maybe I remember there's a one page is good for this for a question as well. So let me remove this. So so this another maybe like just a test of your whether you guys are following me. So let's say I have it's very hard to read, like I mean see, like in this figure here I have three location here. I have this location here, location here, and location here. So let's try to match with the UV. So I have like this EUV value. um of course EUV is a function, right? You think of like you can write U and V, right? So I have this value that is like close to zero in the middle, and then I change around, and I have like something like along this diagonal like is kind of zero, and for the west is like non-zero, and I have the whole thing is like more or less like zero. So which correspond to which? Maybe I just ask one of them. So uh let's say maybe this one. So what is this one correspond to which each of these I mean EUV function? Okay, that's got a D here. What is D? So maybe okay. Okay, I need to write somewhere. Let me try to write, even though I really hate to write on like PowerPoint. This is so silly. Okay, I call this A. Maybe like A here. Oops, and B here. This is a test of my super mouse skill. And C here. So this point here will correspond to like A, B, or C. Oh, thank you. Yeah. So yeah, you have two B's there. Yeah. Okay. Um. So okay. This time the majority is wrong. Um. And so remember like what was EUV again? EUV is like you think of like you shift this like image, right? Yes, actually is. So UV is like when you you try to shift the image somehow, shift the patch somehow, just the patch, right? I shouldn't say the image, shift a patch somehow, and see the patch is the same as before, right? This generate your EUV function. So if I have this patch here, I move around, right? I move around. This is like the whole kind of like for this region here is more or less flat way. So therefore, if I move around here, it shouldn't change much. So therefore, like EUV value for different U and V, for example, I shift like just by one pixel horizontally, it will be more or less zero, and shift up also like more or less zero here. So it has some like changes, but it's compared to the other two, it's like more or less it's a lot less, right? But on the other hand, like for a patch here, you can think of like say has lots of variation. If I shift a little bit, like if I shift a pixel by up or down like a pixel or two, then the value change drastically, right? So then like, if I consider patch move just by a little bit, I might subtract the difference, the square difference, basically like sum over the square differences of those two patches, then I will have something uh non-negative, right? So yeah, that's the actually is A. So I move around like all the direction. Basically, I will have yeah, something like this. So okay, now maybe I get back to some equation here. So then you can use this EUV to specify corner, as I said. So I will just Okay, of course I can do something like really from scratch, just compute this EUV for every pixel, right? But this will be kind of computationally heavy because for each of these XY pixel, I need to compute like difference of like I need to shift the patches around and compute the difference, right? And sum them together. So instead, like I can speed it up quite a bit because I don't actually care like in detail like compute this EUV, right? I just want to see the shape of EUV. So what I'm going to do is I can do something like Taylor series expansion. So to speed it up, so I can have like if you remember like Taylor series expansion, like this is like a very nice line that I don't know where. Okay, okay, like I guess it's originally stolen by Wikipedia and then further stolen by me, I guess. So this is so like for the Taylor series expansion, like you're just trying to expand a function like uh uh around some points right here, like it's trying to expand. I guess it's trying to expand around the function the point like 0 here. So the original function is an exponential function ex here, right? So if I start with like expanding like 0 order, okay, 0 order, I need to wait until 0 order. Okay, you see, it's just a constant term, right? And then first order will kind of approximate linearly, and then second order, of course, approximate quadratically. 0 order, first order, second order, and then we continue to approximate something like that. So and and to approximate like high order, you just first order you okay basically and the 0 order you just need to know like what's the value at that point, right? And the first order you need to know like the derivative at that point, and second order you want to know the change of derivative, and then like so on and so forth. In this case, we just care about the first order really. So then let's see, what do I have here? Oh, okay, here I guess it's probably better to use writing. So I start from here. Let's say have the function here, right? And let me try to expand that. So using Taylor series expansion. So what I'm going to do is I'm going to approximate this part here. This ix plus u y plus v using Taylor series expansion. So assuming u and v are small, right? So it's always like when you approximate using like expansion, like Taylor series expansion, or like yeah. So you are kind of like have this u and v are assumed to be small. Um, oh, actually, because because this is essentially the change, right? This u and v here, right? So if this is big, then the approximation, I mean, what I want to say, if this u and v, like basically like x minus a here is essentially the u and v. If this is more than the higher order term, like will be small, right? So then I can ignore that. So that's okay. Yeah. So yeah, it's an I don't know, like may not be an important remark here, but anyway. So here I am soon like u and v are small, and then I expand this guy. So I have like ix plus u y plus v. So therefore approximately will be like ix y. So I have like two variables here, right? So I should so therefore like actually I need to kind of like uh, expand along two directions. So have like two derivative here, two partial derivative here. So ixy partial derivative with respect to x, u plus xy with y times 3 here. Okay, maybe I shorthand here as ix, and this iy. This is partial derivative like in the x direction and y direction. So in practice, this is just a computer derivative image, right? So for example, like last time when we talk about edge detector, we can use the derivative of Gaussian, or like actually in OpenCV they just use the Sobel filter like to compute the derivative. If you remember the Sobel filter is like something like this, like 1 0 0 1 2 1 minus 1 2 minus 2 minus 1, something like that. and maybe I have like 1/4, I guess, like something like that. That's the sorbet filter. Um, to approximate the derivative, this will be the okay. This is x and y direction. This is a question from last time, but uh, so this is like a derivative of, is that ix or iy for this one? So if I want to take derivative of this guy, I should have an image that going to be filtered by this guy. Basically, will filter by this guy. Maybe I just say why like this, or like simply like this will filter with this, because this is like doing a convolution on this filter here. Yes, it should be for this particular filter. It should be like derivative in ES. Good. So yeah, this is a derivative in the IX direction. So yeah, okay, great. So um let's continue. So I have this here. So we can, okay, yeah, maybe I shouldn't erase it yet. So I can tell a series expand this expression like with this guy here, and then like this can be just computed with sorbet filter. Okay, let's substitute back into this EUV here. So I have EUV. So therefore it's equal to sum over WXY. And like this, you see I have IXY got cancelled, right, with this guy, right? So I just have this derivative back. So I have like basically IXU plus IYV square, right? So note that like this expression is always positive for no matter U and V, right? Because this way is always positive, right? This guy is positive. The window is supposed to be positive. It's like a low pass filter. So all the coefficients supposed to be positive. Um, well, maybe I didn't mention that, but yeah, low pass filter is supposed to be like that. Um, and so yeah, so therefore like this in general EUV, uh, yeah, is positive. Yeah, yeah. I mean this expression in general is positive. And then like here I can rewrite in a kind of matrix form here. Hopefully it won't be too funny for you guys. So this is a square, right? Square of the same thing, but what's inside I can just write as a ix iy times u and v, right? I'm actually I can even write like this. Because this is actually equal to like u and v times ix iy. I may write like u v ix iy and then ix iy u v, right? Note that this is the same, right? This is both of them is equal to this guy, right? So I just repeat this 2 times. But if I write like this, I have this is like a matrix here. I have like ix. Maybe I just want me to say the thing in the middle here is actually just a matrix ix iy ix. Actually, ix is just ix iy and iy, right? And then like I can have u and v pull out as well. So I can pull outside the summation here. And so I will have something like this. I will have like u and v, sum over x and y, wxy, ix iy, x, sorry, ix ix, ix iy, ix, y iy. This is u and v here. So this matrix here, let me just call it M. And note that like M is a positive definite. So if okay, if you don't know what I mean is kind of okay. Like so what for the positive definite matrix, it means that like for a matrix M, I put in any value U and V here, or like pick any value, maybe I this time I call it X and Y here. Have this quadratic form, like this will give me a number, right? If for any f x and y here, I have this one is like bigger than equal to 0, then it's called like positive. Actually, more precisely, it'll be positive semi-definite. In this case here, like because I know from the beginning this value like is always bigger than equal to 0, right? So therefore, like this is positive definite, positive. So and we know like actually like sometime before, like I guess when we talk about Fourier transform, actually we kind of mentioned that with positive definite matrix, then the eigenvalue will be real, and also like can be diagonal. Actually, most important in this case, M can be diagonalized with an orthogonal matrix. Orthogonal matrix is actually just a rotation. So what I mean is like you can have like mx is equal to lambda x, and then I can have like two different eigenvalues. This is m is 2 by 2, right? So I can have like two different eigenvector and eigenvalues. So and sorry, like this with x1 here, x2 like let's say lambda 2 x2. Basically, I have two eigenvectors at x1 and x2. I'm like with two eigenvalues lambda 1 and lambda 2. And I can have like x1, x2 are orthogonal and normalized. So basically, x1 transpose x2 is equal to 0, and also like x1 transpose x1, x2 transpose x2 is equal to 1. So then, therefore, if I rearrange that, I have mx1, x2 equal to x1, x2, lambda 1, lambda 2. So you can verify that. So this is actually the same as these two equations. I just write that as one equation here. And then like this will be an orthogonal matrix. I can call it R here. It's actually just a rotation because if you look at R transpose, it will be just give you one identity. For example, I can verify that like R is x1, x2, right? R transpose is x transpose, y transpose. Or maybe I better like do the uh, do it this direction. Yeah, even though it's still like identity, maybe this direction is easier to illustrate. So I have like x1 transpose, x2 transpose, x1, x2. Then this actually give me like x1 transpose x1, x1 transpose x2, x2 transpose x1, and x2 transpose x2. And as we said here, right, x1 transpose x2 is 0, right? So these two are 0 actually. And this 2 is 1 because of here. So here I go a little bit quick because I depends on your background. Uh, you may or may not follow me honestly. So but for graduate students, I expect you're able to follow me. So but my point is that like okay, this M here can be diagonalized by this R here. So and I will have like MR is equal to R lambda, and so MR inverse is just equal to, so therefore R inverse MR is equal to lambda 1, lambda 2, and also like this is actually lambda inverse R inverse is just equal to R transpose because R is orthogonal, so I have this here. Now I put this back, so hopefully the main thing is I can do this. And then I can put it back here. Now for someone that like cannot follow like what I'm talking about earlier, so this is the important part. I can do that. So since I can do that, given that M is a positive definite, now I put it back here. So I have like UV R transpose M R and UV here, right? Oh sorry, wait a second. Oh sorry. I have like UV. Let me write this back first. UV, something like that, right? This is, but don't forget about it. This is basically the approximate version of our EUV here. as I said, like as we said, like we don't want to compute EUV uh, exactly, right? We just care about the shape. So then we approximate this EUV as this guy here. Now, because my M can be diagonalized like this, so then I have like M actually is equal to lambda 1, lambda 2, R transpose, right? Just multiply by R and R transpose on both sides. So I have like this instead. So now this guy I can substitute into here. So I will have like equal to UV R lambda 1, lambda 2, R transpose UV. And note that this is just rotation. So I can group together. This is R uh, transpose UV, and this is a R transpose UV transpose lambda 1, lambda 2. So I can define R transpose UV as like, let's say U pi V pi. And note that like this is actually just a rotation. So it's like I have a UV axis originally. It's like this. I have UV axis. Now I rotate a bit like into U pi V pi here. I have U pi V pi, new rotation, my new axis. And in terms of this new axis, I have a kind of a quadratic function. Like this is actually lambda. So therefore I have like U pi V pi lambda 1, lambda 2, U pi V pi. And so finally my EUV is just something like lambda 1 U pi square plus lambda 2 V pi square. And U pi V pi again is like just rotated version of U and V here. So what's this? I mean like let's say if I have this is equal to 1, this is just a okay, let's say if lambda 1 is if lambda 1 and lambda 2 is bigger than equal or even like bigger than 0. So do you know like is that maybe I'll give you some choice here. Ellipse, hyperbola, is a parabola? I don't know. I'm sorry, like so this is like some like maybe like uh I don't know whether okay yes which one is that, like it's a question like if I have lambda 1 and lambda 2 bigger than 0. Yes, it's just a ellipse. Like this is a ellipse. If you know ellipse is something like that, right? So it's like what we have is just ellipse shape ellipse here. I'm not why I can say lambda 1 and lambda 2 is bigger than 0, because we start with knowing that EUV has to be bigger than 0, right? Because with that is a positive definite. So therefore, like this value here, if like lambda 1 and lambda 2 is either of them is negative, then this guy can be negative, right? So actually what we get is that we eventually approximate UUV into simple ellipse. And the ellipse is specified by this lambda 1 and lambda 2 here, which is basically the eigenvalue of M here. Now, okay, I guess I could have confused some of you, but I hope you get the big picture here. But just let me see. So okay, that's what I'm repeating like here a little bit is like I have this M here. So E is approximated with this guy, right? And then like the M function is like this one, and you can actually for this IXX, IXY and so on can be just computed with the Sobel filter and so on, and And with the windows, it's like actually you can just think of like this window and another low pass filter. So therefore, like you can compute it as like uh, applying a gradient filter. Or like actually at the what's that? Like yeah, apply gradient filter and then like uh and then apply low pass filter here. Um, and then for the m value here, as I said that uh this m here, I can diagonalize that. So if I rotate, essentially I rotate, actually this actually is, yeah. If I rotate along this direction here, so I basically get a ellipse here. And the shape of the ellipse is kind of like governed by this lambda 1 and lambda 2 is actually just the eigenvalue of m. Um, and now, yeah, yes, actually I just flash a little bit. So now let's go back to maybe a Leah final question, I guess. Now let's summarize what we have. Like, okay, this is basically, we start with the EUV here. We start with EUV here. And we know that like if EUV is rough, I mean, in the sense that if you change UV along different direction, if you have EUV changes a lot, then it is likely to be a corner. If EUV is flat, then it's going to be a a so I mean it's going to be flat, basically a smooth surface, smooth region. And then we say that we can eventually approximate EUV as something like that. Something like that. And basically U pi and V pi are just rotated version of U and V. Actually, along the eigenvector, actually U pi and V pi really are just the eigenvector there. So, but that's okay. We only care about the lambda because we want to know how fast this UVM changes, right? So now my question is like, okay, I know that for corner, EUV changes a lot, right? This is our common, change a lot. That will be a corner. That will indicate that's a corner. So, so then like I only have like to specify now. I kind of like boil down this EUV with only two parameters, lambda one and lambda two. Right? So lambda one, lambda two. Let's try two different several situation here. Lambda one and lambda two very large. Lambda one very large and lambda two close to zero. Lambda one and lambda two both close to zero. So which one is corner? This is A, B, and C here. So which one is corner? Wait. Actually, B is the most not likely one. I don't know why so many of you guys pick B. So, uh, so actually, let me call like other two cases also. Um, so if EUV change a lot, it will be corner. Maybe I use a different color. If EUV, if for edge will happen. EUV change a lot, only one direction, in one direction. And then in other direction, it doesn't change much. And then I have like, if I smooth vision, so I guess this is the end, over time, but let's finish this question. Smooth vision, will be UV doesn't change, right? UV is close to zero. So which one? A, B, and C. Okay. Yeah, A or C, like actually basically I would say. So, but be careful, like look at this function here. What values are likely to get? Oh, actually, like, probably you guys are correct. Actually, I'm thinking like the other way around. Yeah, you guys are correct. So yes, lambda 1 and lambda 2 are big, then like you will be likely to be corner, right? Because like this is big, then like you will, if I, yeah, basically I change whatever UV direction. So B will be edge. This will be an edge. So actually, more precisely, it would be like an edge in the in let's see, in the U2 in the U2 sorry, in the V direction. So if like this is the eigenvector for the V pi, okay, in the V pi direction, basically this is U pi here. So along this U pi direction, you're going to change a lot, right? But on the V pi direction, you're not going to change. So therefore, it's actually an edge there. So I guess okay, I take a bit more time, right? So I mean for the demo. So I guess I will come back to that like maybe next time. So but I'm almost done for this. I guess I'll just give a quick review next time and then like talk about something else. So I'll see you guys next week. But I'll wait a bit like in case you guys have any questions. So and
I have a question on the homework.
yes.
So I have two images, and one of them is like too big for the second one, and so I'm trying to resize them. And when I
Oh,
check the dimensions, they're both kind of like the second image that's actually smaller than the first image
yes.
is actually bigger dimension than the first image. So I'm unsure of like I was trying to like crop the first image to possibly get it the same size, but if the second image is actually bigger than the first image, I don't know how to. Jupyter Notebook is just showing the second image as smaller than the first image.
That I don't quite get it, but I guess you can just resize that. And maybe I will let you share the screen, then I can see what I see.
Oh well, I have it on a different computer,
Oh,
but
okay,
I
yeah.
can send you like a
Okay, yeah,
on Discord.
yeah. You may send me on Discord then, like maybe, yeah,
Okay,
yeah,
all right, thank you.
yeah, sure. So okay. Any other questions? So yeah. If not, I guess I'll see you guys next week then. Yeah.